Have you ever looked at the bottom of an aquarium and wondered if that layer of sand or gravel is doing more than just sitting there? Most people see substrate as decoration, a way to make the tank look natural, or hide the glass bottom. But what if the key to a thriving aquarium ecosystem has been hiding in plain sight all along, right beneath our fish? Every grain of sand, every piece of gravel, every particle of specialized soil is actually part of an invisible engine that keeps aquatic life flourishing. This seemingly inert material at the bottom of your tank is actually teeming with billions of microscopic workers, chemical processes, and hidden creatures that form the backbone of aquarium health. Today, we're going to explore the remarkable truth about aquarium substrate and its critical role in natural filtration. The substrate in your aquarium is performing tasks that would cost hundreds of dollars in equipment to replicate. It's breaking down waste, converting toxins, housing beneficial organisms, and creating chemical gradients that mirror processes found in natural rivers, lakes, and ocean floors. By the end of this documentary, you'll never look at that layer of material at the bottom of an aquarium the same way again. When we set up an aquarium, we often focus on the flashy elements: the fish, the plants, the decorations, the filters. But beneath it all lies the substrate, quietly performing functions that are essential to the entire system's survival. This foundation layer is far more than a decorative element or a surface for plants to root in. Think about natural aquatic environments for a moment. Rivers flow over beds of sand and gravel. Lakes have layers of sediment accumulated over centuries. Ocean floors consist of various materials from fine silt to coarse rubble. These substrates aren't just passive surfaces. They're active participants in maintaining water quality and supporting life. The same principles apply to our aquariums, but in a much more concentrated and critical way. In nature, substrate surfaces provide attachment points for biofilms, complex communities of bacteria, algae, and other microorganisms. These biofilms form the base of aquatic food webs and drive nutrient cycling. When we add substrate to an aquarium, we're essentially creating millions of tiny surfaces where these same processes can occur. A single handful of aquarium gravel contains more surface area than the flat bottom of the tank could ever provide. The relationship between substrate and water quality begins the moment water touches those surfaces. Beneficial bacteria immediately begin colonizing every available surface, creating a living filter that operates 24 hours a day. Unlike mechanical filters that simply trap debris, substrate-based biological filtration actually transforms harmful compounds into less toxic forms through bacterial metabolism. Within days of setting up a new aquarium, an invisible city begins to form on every grain of substrate. Beneficial bacteria grow not only in filters, but also on every surface in the aquarium, including gravel, glass walls, and decorations. These microscopic organisms are the true heroes of aquarium filtration, and substrate provides them with prime real estate. Two general types of beneficial nitrifying bacteria are required for the nitrogen cycle: Nitrosomonas species that use ammonia as a nutrient source to produce nitrite, and Nitrobacter species that use the nitrite nutrient source to produce less harmful nitrate. These bacteria require surfaces to anchor themselves, and substrate provides exactly that. Millions upon millions of attachment points. But how do these bacteria actually colonize substrate? The process is fascinating. Nitrifying bacteria are classified as obligate chemolithotrophs, using inorganic salts as an energy source and oxidizing ammonia and nitrites for their energy needs, while fixing inorganic carbon dioxide to fulfill their carbon requirements. They're largely non-motile and must colonize surfaces for optimum growth, secreting a sticky slime matrix to attach themselves. The bacterial colonization of substrate doesn't happen uniformly. Different species occupy different niches based on oxygen availability, nutrient concentrations, and competition with other microorganisms. Near the substrate surface, where oxygen is plentiful, aerobic bacteria dominate. These are the workhorses of the nitrogen cycle, converting ammonia to nitrite and nitrite to nitrate. But as we go deeper into the substrate layers, something interesting happens. Oxygen becomes scarce, and different types of bacteria take over. Microbial colonization can be visualized mainly within the outer periphery of surfaces, with environmental scanning electron microscopic observations suggesting an extracellular polymeric substance-rich matrix and submicron-sized bacterial cells. This biofilm structure is crucial because it protects the bacteria from environmental stresses and creates microenvironments where different chemical processes can occur simultaneously. The nitrogen cycle is perhaps the most critical chemical process in any aquarium, and substrate plays a starring role in this continuous performance. Fish release waste in the form of ammonia, which is toxic to all aquatic organisms. And this ammonia, along with waste from uneaten food and dead plant material, must be processed to maintain a healthy environment. Here's where substrate becomes crucial. When choosing biofilter media, it's important that enough surface area is provided for biofilm and beneficial bacteria to grow on, as you want extra capacity for biofilm growth in case there's an upset to the system. Every grain of substrate acts as a mini biofilter, hosting the bacteria that drive this vital process. The journey begins when fish excrete ammonia through their gills and in their waste. This ammonia dissolves in the water and comes into contact with substrate surfaces colonized by Nitrosomonas bacteria. By the third day after adding fish to a new aquarium, ammonia levels typically begin to rise, and by the second week, nitrite levels should be rising as the bacteria population grows. But the nitrogen highway doesn't stop at nitrate production. In deeper substrate layers where oxygen cannot penetrate beyond about 2 inches, anaerobic conditions develop, allowing denitrifying bacteria to grow and use nitrate as their oxidizing agent instead of oxygen. This process, called denitrification, converts nitrates into nitrogen gas, which harmlessly escapes into the atmosphere. The efficiency of this nitrogen highway depends heavily on substrate characteristics. Particle size, depth, and porosity all influence how effectively the nitrogen cycle operates. Fine sand creates different conditions than coarse gravel, and each material supports different bacterial populations and processes. Understanding these differences is key to optimizing substrate for specific aquarium needs. Not all substrates are created equal. The choice between sand, gravel, or specialized aquarium soil can dramatically impact your aquarium's biological filtration capacity and overall ecosystem health. Each material brings unique properties that affect everything from bacterial colonization to water flow patterns. Let's start with sand, one of the most popular choices. Sand gives tanks a smooth, natural look and doesn't trap debris as much as gravel, helping to keep water clean, making it especially suitable for fish that like to dig, such as cichlids or catfish. The tight packing of sand particles creates unique conditions for bacterial growth. The ultra-fine nature of sand prevents debris from falling between gaps and causing bacterial buildup, ensuring that toxic waste rests on top of the sandy surface, to be removed manually or picked up by aquarium filters. Gravel, on the other hand, offers different advantages. Gravel provides superior drainage and harbors beneficial bacteria essential for ensuring water quality in tanks, with its diverse texture and structure, creating ample surface area for bacterial colonization. The spaces between gravel particles allow for better water circulation, ensuring oxygen reaches deeper layers and supporting aerobic bacteria throughout a greater depth. Then, there's specialized aquarium soil, which takes biological filtration to another level. Unlike gravel or sand, aquarium soil is full of nutrients that help plants grow strong and fast, while helping keep water pH levels stable and improving water quality. Many aquarium soils are designed with high cation exchange capacity, meaning they can hold and slowly release nutrients, supporting both plant growth and bacterial communities. Natural porous media are hierarchical in structure, with corresponding length scales spanning several orders of magnitude from submicron to millimeter length scales, and coarser substrates like gravel allow food and waste to fall through, making it easier to vacuum, while finer options like sand can compact easily and trap debris. The porosity of substrate material is perhaps its most underappreciated characteristic. Internal porosity can positively affect microbial colonization and activity, with mineral coatings on filter materials showing porosities up to 8 times and specific surface areas up to 11 times higher than uncoated sand. This massive increase in surface area translates directly to increased biological filtration capacity. One of the most fascinating aspects of substrate filtration occurs in what aquarists call the deep zones, those layers far beneath the surface where mysterious chemical processes unfold. Deep sand beds work because of denitrification, with the oxygenated top 1–2 inches housing aerobic bacteria that convert ammonia into nitrite and then into nitrate, while the anaerobic layer below 3 inches provides a low oxygen zone where anaerobic bacteria break down nitrates into nitrogen gas. The creation of these anaerobic zones requires specific conditions. To achieve an anoxic environment in the substrate, water must flow through at a very slow rate, with aerobic bacteria and organisms using up the oxygen in the water before it reaches the anoxic region. If water flows through the substrate too quickly, these special conditions never develop. But how deep does substrate need to be to create these beneficial anaerobic zones? For effective denitrification, a deep sand bed needs to be at least 4 to 6 inches deep, as shallower depths won't develop those critical anaerobic zones. The grain size matters too. Fine sand at 2 inches depth can provide an anoxic environment for anaerobic bacteria to reduce nitrate, while coarser substrates may need to be deeper to achieve the same effect. The bacteria living in these deep zones are remarkably different from their surface-dwelling cousins. Anaerobic bacteria live in areas devoid of oxygen and use the oxygen attached to nitrate to respire, which frees up nitrogen gas that can escape into the atmosphere. This process completes the nitrogen cycle, actually removing nitrogen from the system rather than just converting it to less toxic forms. However, deep substrate beds require careful management. Stirring and vacuuming to disrupt anaerobic pockets makes sand beds less productive by disrupting bacterial population activity. And if oxygen is introduced to anaerobic and anoxic zones, denitrification and iron and manganese reduction comes to a stop. This delicate balance between maintaining these zones while preventing harmful conditions requires understanding and respect for the processes at work. There's been considerable debate about whether harmful gases can build up in deep substrate beds. While some hobbyists claim that disturbing soil in aquariums releases poisonous hydrogen sulfide gas, the gas is actually harmless carbon dioxide created when bacteria decompose organic matter. Modern research suggests that in properly maintained aquarium substrates, dangerous gas buildup is largely a myth. Beyond bacteria, substrate harbors an entire ecosystem of microscopic and near-microscopic organisms that contribute to aquarium health. This hidden world of microfauna transforms substrate from a simple filter medium into a complex, living ecosystem that mirrors natural aquatic environments. Copepods and amphipods feed on algae, detritus, and uneaten food, helping to keep tanks clean and reducing waste while providing a natural food source for fish and invertebrates. These tiny crustaceans are often invisible to the casual observer, but play crucial roles in nutrient cycling and waste management. Within the substrate itself, a different community thrives. Small, harmless worms, such as detritus worms and nematodes, live within the substrate, feeding on decomposing plant matter and organic debris, breaking down organic material and aerating the substrate. While some aquarists view these organisms with suspicion, they're actually beneficial members of the aquarium ecosystem. The diversity of life in substrate is astounding. Benthic microfauna includes aquatic worms, snails, and various other organisms, with the substrate providing numerous microhabitats where these creatures can thrive. Each species occupies a specific niche, contributing to the overall health and stability of the aquarium. These organisms don't just consume waste, they process it in ways that make nutrients more available to plants and other organisms. Microfauna help break down waste, support the nitrogen cycle, and prevent toxic buildup, serving as food for fish and invertebrates while improving the aesthetic appeal and ecological balance of the tank. Their activities create a more natural and self-sustaining ecosystem. The substrate also serves as a nursery for many of these organisms. Copepod populations create layered defenses with surface cleaners, preventing biofilm growth, midwater filterers stopping suspended particles, and substrate specialists breaking down decaying matter. This multi-layered approach to waste management is far more effective than any single filtration method. What's remarkable is how these organisms find their way into our aquariums. These tiny organisms most likely transfer into aquariums through plants, substrate, decor, or even fish or invertebrates, establishing populations that become beneficial parts of the tank's ecosystem. Once established, they create self-sustaining populations that require little to no intervention from the aquarist. The secret to substrate's filtration power lies in a concept that's invisible to the naked eye's surface area. When we look at a handful of gravel or sand, we see individual particles. But at the microscopic level, each particle is a vast landscape of peaks, valleys, and pores that provide homes for billions of bacteria. Gravel allows for better water circulation within tanks, ensuring oxygen is distributed evenly. And waste is efficiently removed, with gaps between gravel particles creating space for beneficial bacteria to colonize and perform biological filtration effectively. These spaces between particles are just as important as the particles themselves. The relationship between substrate particle size and surface area is counterintuitive. Smaller particles packed together actually provide more surface area per unit volume than larger particles. Different sizes, shapes, and colors of substrates exist, but most fall under three types: gravel, sand, and soil, each with different surface area characteristics. Fine sand might have 10 times the surface area of coarse gravel in the same volume, but surface area alone doesn't tell the whole story. The ability of bacteria to colonize and grow on different surfaces is essential for biofilm development, with substrate stiffness and porosity affecting how bacterial colonies expand and establish themselves. The physical and chemical properties of the substrate material influence how readily bacteria can attach and how thick biofilms can grow. Modern specialized filter media takes surface area to extremes. Advanced biological media can have porosity of approximately 42%, providing great usable surface area for bacterial colonization, with some materials allowing both nitrifying aerobic and denitrifying anaerobic bacteria to grow throughout their unique structure. These engineered materials can provide hundreds of times more surface area than traditional substrates. The flow of water through and around substrate particles creates microenvironments with different oxygen levels, nutrient concentrations, and pH values. Biofilms contain not only immobile water, but also considerable amounts of mobile water, with the total percentage of water in biofilms as high as 97%, containing channels and voids that facilitate advective transport. This complex structure allows multiple biological processes to occur simultaneously in very close proximity. Understanding surface area helps explain why established substrates are so valuable. Over time, mineral coatings and biofilms can dramatically increase the effective surface area. The amount of mineral coating correlates positively with internal porosity, packed bulk density, and biologically available surface area of filter material, with volumetric ammonia removal rates also increasing with the degree of mineral coating. Choosing the right substrate for your aquarium is both an art and a science. The decision impacts everything from the types of fish you can keep to the long-term stability of your ecosystem. Understanding how different substrates perform in various situations helps create thriving aquatic environments. When choosing between sand and gravel, think about what your fish need and how you want your tank to look. Sand is great for fish that like to dig and sift, while gravel offers stability and is easier to clean with a vacuum. But the choice goes deeper than just fish preferences. For planted aquariums, substrate selection becomes even more critical. Using aquarium soil substrate in planted tanks is key to a lush, beautiful scape, as artificially dyed gravel or sand have no nutrients for plant roots to absorb. And even with root tabs, they're simply not long-lasting options for keeping a healthy planted aquarium. The substrate must support both root development and bacterial colonization. The bioload of your aquarium should influence substrate choice. Heavy bioloads require substrates with maximum surface area for bacterial colonization. Major changes in an aquarium's bioload affect the bacteria population. Adding several new fish at once may require an increase in nitrifying bacteria to deal with increased pollution. Substrates with higher surface areas provide buffer capacity for these fluctuations. Water flow patterns in your aquarium also matter. Sand prevents debris and waste products from sinking into your substrate, instead keeping them on the top layer where your filter intake can grab and remove them, though the small diameter of sand grains prevents water from flowing through, creating dead zones where oxygen has been depleted. Understanding these trade-offs helps match substrate to filtration systems. Different fish species have evolved with specific substrate preferences. Bottom-dwelling species like Corydoras catfish require smooth substrates that won't damage their barbels. Cichlids that sift through substrate need fine materials they can safely process. Selecting appropriate substrate for your aquarium is crucial for the well-being and visual appeal of your aquatic habitat, considering the requirements of your fish species and the aesthetic you wish to achieve. Consider maintenance requirements when selecting substrate. With gravel, waste seeps down into it, so you have to vacuum it all out, potentially missing some and harboring nitrates, while with sand, all waste sits right on top. Just hover your siphon right above the sand, and it picks everything up. Your maintenance routine and schedule should align with your substrate choice. A substrate's effectiveness as a biological filter depends on proper maintenance, but this does not mean aggressive cleaning. Understanding how to maintain substrate while preserving its biological function requires a delicate balance between cleanliness and bacterial preservation. Not disturbing the sand is critical because stirring and vacuuming disrupts anaerobic pockets, making sand beds less productive by disrupting bacterial population activity. This principle applies to all substrates. Overzealous cleaning can destroy months or years of biological development. The key is understanding what needs cleaning and what should be left alone. Surface debris and accumulated waste should be removed regularly, but deep cleaning that disturbs established bacterial colonies should be avoided. Using sand substrate minimizes the need for frequent in-depth cleaning, as the ultrafine nature prevents debris from falling between gaps, ensuring toxic waste rests on top of the surface. Water changes play a crucial role in substrate health. Once nitrates are being produced and ammonia and nitrite levels are at zero, routine partial water changes of about 10% per week should keep nitrate levels within a safe range. These water changes remove accumulated nitrates while preserving the bacterial colonies in the substrate. Long-term substrate maintenance involves monitoring for compaction and channeling. Over time, fine substrates can become compressed, reducing water flow and creating anaerobic pockets where they shouldn't exist. Compacted gravel restricts oxygen flow to the substrate, potentially suffocating beneficial organisms, reducing oxygen levels, and limiting the movement of essential resources. Some aquarists practice substrate supplementation, adding beneficial bacteria or minerals over time. Commercial bacterial supplements contain live cultures of nitrifying bacteria, perfect for jumpstarting the nitrogen cycle by colonizing filter media, substrate, and other surfaces. These supplements can help maintain bacterial populations, especially after medications or other disruptions. The age of substrate matters too. Consider partial sandbed replacement every few years to maintain efficiency, replacing no more than 20-25% of the sand at a time to avoid disrupting beneficial bacteria. This gradual renewal maintains biological function while preventing the accumulation of compounds that can affect water chemistry. Temperature and pH stability are crucial for substrate bacteria. Nitrifying bacteria are most active at temperatures ranging from 68 to 86 degrees Fahrenheit, with metabolism decreasing below 50 degrees and levels above 95 degrees being potentially life-threatening. Maintaining stable conditions ensures consistent biological filtration. As we look toward the future of aquarium keeping, substrate technology continues to evolve. Researchers and manufacturers are developing new materials and methods that enhance the natural filtration capabilities we've explored throughout this documentary. Engineered substrates are pushing the boundaries of what's possible. Materials with controlled porosity, specific mineral content, and optimized particle sizes are being developed to maximize biological filtration while minimizing maintenance. Modern biological media creates optimal environments for beneficial bacteria to thrive, supporting both aerobic and anaerobic bacteria across various filter types and flow rates. The integration of substrate with other filtration methods is becoming more sophisticated. Rather than viewing substrate as separate from mechanical and chemical filtration, modern aquarium design considers how all these elements work together. Substrate is increasingly recognized as the foundation of a holistic filtration approach. Research into microbial communities continues to reveal new aspects of substrate biology. Scientists are identifying previously unknown bacterial species and understanding their roles in nutrient cycling. This knowledge is leading to more targeted approaches to establishing and maintaining beneficial bacterial populations. The role of substrate in planted aquariums is expanding beyond simple root anchoring. New soil-based substrates are being developed that provide long-term nutrient release while maintaining optimal conditions for both plants and bacteria. These substrates can maintain stable parameters for years without replacement. Climate change and environmental concerns are influencing substrate choices. Sustainable materials, locally sourced substrates, and alternatives to mined materials are becoming more popular. Aquarists are increasingly conscious of the environmental impact of their hobby, including substrate selection. Biotechnology is opening new possibilities for substrate enhancement. Probiotic treatments, enzyme additions, and targeted bacterial inoculants are being developed to optimize substrate performance. These biological tools work with natural processes rather than replacing them. As we come to the end of our exploration into the hidden world of aquarium substrate, let's take a moment to appreciate the remarkable complexity we've uncovered. What started as a simple question about the material at the bottom of an aquarium has revealed an entire universe of biological processes, chemical reactions, and microscopic life. We've learned that substrate is far from inert decoration. It's a living, breathing component of the aquarium ecosystem that performs multiple critical functions. From hosting billions of beneficial bacteria that drive the nitrogen cycle to providing homes for countless microscopic organisms, substrate is truly nature's hidden filtration system. Every grain of sand, every piece of gravel contributes to a complex biological filter that operates continuously, converting toxic waste into harmless compounds. The bacterial cities we explored show us that the most important inhabitants of our aquariums might be the ones we never see. These microscopic workers process waste, cycle nutrients, and maintain water quality with an efficiency that no mechanical filter can match. The deep zones within substrate, with their mysterious anaerobic processes, complete the nitrogen cycle in ways that mirror natural aquatic systems developed over millions of years. We've discovered that choosing substrate isn't just about aesthetics. It's about creating the right conditions for biological processes to thrive. Whether it's the fine sand that creates anaerobic zones for denitrification, the gravel that provides extensive surface area for aerobic bacteria, or the specialized soils that support planted tanks, each substrate type brings unique benefits to the aquarium ecosystem. The microfauna living within substrate remind us that diversity is strength in biological systems. From copepods to detritus worms, these tiny organisms form food webs, process waste, and contribute to the overall stability of the aquarium. They transform substrate from a simple filter medium into a complete ecosystem. Perhaps most importantly, we've learned that successful aquarium keeping isn't about controlling nature. It's about working with it. By understanding and supporting the natural processes that occur in substrate, we can create aquariums that are more stable, require less maintenance, and provide better environments for our aquatic pets. The next time you look at an aquarium, take a moment to appreciate what's happening beneath the surface. In that layer of substrate, billions of organisms are working together in an intricate dance of chemistry and biology. They're converting waste, cycling nutrients, and maintaining the delicate balance that allows aquatic life to thrive. It's a reminder that in nature, as in our aquariums, the most important processes often happen where we least expect them, right beneath our feet, or in this case, right beneath our fish. Thank you for joining me on this journey into the hidden world of aquarium substrate. If you found this documentary informative, please consider giving it a thumbs up and subscribing to the channel for more in-depth explorations of aquarium science. Share this video with fellow aquarists who might benefit from understanding the critical role substrate plays in their tanks. And remember, the key to a successful aquarium might just be hiding at the bottom, quietly doing its job, one grain at a time. Until next time, keep learning, keep observing, and keep appreciating the remarkable complexity of the aquatic worlds we create. Thank you for watching and happy fish keeping!